I'd say go ahead. Uh,
Yeah. Okay.
Mr. Yeah.
So the topic of the session, reusable code. I tried to include some examples that are that should be possible, or at least should explain generics and the principles of developing reusable code, tech stack independent. I will be using TypeScript in my examples, but you should be able to extrapolate it into your own language that you are developing in. First off, um, a misconception that I've heard often in the past few years is that every scenario or entity is different, so I can't build reusable services. I've used it once in a I've heard it once in a while. Um, I think you can. You just need to be able to find a way to extrapolate the logic of what you're trying to do to a higher level. So you can, but of course you can't always extrapolate everything. Um, so first, let's do an example on calculating the sum of something. So we have a given set of items for which we want to calculate a sum. So if we have a look at these two interfaces, so we have a car interface which has some properties and a door count, and we have a meeting room interface also with some properties and a capacity. Um, we have a set of items, uh, some cars, some meeting rooms, and we want to know the sum of the amount of doors for the cars, and also we want to count how many or what the total capacity of all the meeting rooms is. So what we would do in the left scenario is we would write a function, we would pass it the cars, which is typed to being an array of cars, and our return type is a number being the total count of doors. Then the implementation itself, just calculate everything, and when we are adding something to the sum, we want to add the door count. So door count is a property specific to the car interface. This means that this function can't be used to calculate the capacity of our meeting rooms. So to calculate the capacity of our meeting rooms, what would we do then? Pass it an array of items being an array of meeting rooms. Again, a number is being returned, being the sum of the capacity. Again, the implementation, and in this case, room.capacity to add the capacity of that room to the sum. So at first glance, these are two separate sum functions that aren't that reusable, because the only thing that you can pass to them is a set of meeting rooms. They have this explicit number that is being added to the sum that is totally dependent on the interface of the items that are being passed to the function. So I can't pass an array of cars to this function, because then the TypeScript compiler would complain that it doesn't match the meeting room interface, and the other way around. If you were doing this in JavaScript, for example, where there's no compiler, I think this would start adding undefined, and the total sum would be 0, because 0 plus undefined is still 0, I think. So then we will get runtime issues, and that's not something that we want. So in TypeScript, this being typed, we can use generics to extrapolate this into a single sum function. So if you have a closer look at both the sum functions to add the door count together and the function to calculate the total capacity, we notice that we have this syntax going around. So we have the sum of an array of items. We are looping over that array of items, and then we are adding the value of a certain property to the sum. So this frame is the same for both the sum function to add the cars and the sum function to add the meeting rooms. So this means that there is a possibility to extrapolate this to a higher level. The first step, for now, we are just going to ignore type safety in the first step. The function needs to know two things: the array of items that it should loop to calculate the sum, which we already were passing as the first parameter of the function, and how it should retrieve the value of an instance in the set of items so that it can add that value to the sum that it already calculated. So for that, we can introduce a new parameter, the item value function, which is typed to a function accepting a single parameter and returning a number. So if you have a look at the implementation, then we still have the same syntax. So we pass it an array of items. We loop over the items. And when we are looping over a single item, we want to add the already calculated sum to the function that will be returning the value of that instance that should be added to the sum. And we start off with 0 again. So if we were going to use this function, then we can count the number of doors, being as a first parameter the sum of cars, and when we are looping over a single car, we want to return the doors property so that this value can be added to the sum. So this will result in the same amount of doors as we had in the previous step. And immediately, as you can see, we can also use this function to pass it the meeting rooms. And for every room, we want to return the capacity. So right here that it can add the capacity to the total sum, which will result in the same capacity as before. But still, I said right here, let's ignore type safety for a second. The issue right now is that this is not type safe. We can still pass it any array, which might cause some issues, because any accepts literally any type. So that means that the first parameter, the array of anything, can be an array of mixed value types. So it could contain both strings, numbers, objects, nested arrays, which would cause runtime issues when we run the code. So how can we fix these issues? We know that the items in the array will always be of the same type. We are calculating a sum of doors for a car. So all instances in the cars array will always match the interface of a car. The item parameter passed to the item value function, so this one, will always be an instance of something that is in the array. So we know that this is of a certain type, always. So this will be of the same type as the items in the array. So this is the same. So right now we can use some generics. Let's bring in the magic T. So by providing this syntax to the signature of the function, we basically tell the TypeScript compiler or any other compiler, this is generic. And we want to use the generic type T here to specify that the items in the array are of a type T and the item is of the same type. So the TypeScript compiler right now knows this is the same type. It doesn't know or doesn't need to know what the type is right now. And it also doesn't need to know because there's no interface specific logic being used within the function. It's just our type safety measure that we implement to make sure that when I enter car.doors right here, that it doesn't give me a compile issue when compiling the code or any runtime issue. So the usage of the function is still the same, but we get IntelliSense here on car, so we can specify the doors property. If we were to use a different property that doesn't exist on the car interface, then the TypeScript compiler would start complaining, and it helps us from creating bugs in the code that only are discovered runtime. So that's how it can help us enforcing type safety, and as you noticed, we can extrapolate code that at first glance doesn't look to be reusable. A second example, the functionality that is being requested is a reusable interface for typing functions properties to be of a certain type, but on a higher level. So we want to enforce some properties or functions with dynamic types. So the scenario, we need to implement multiple services that are capable of creating an instance. So again, for our cars and meeting rooms, we have a save instance function that accepts an instance and posts it to the HTTP client, which in case of the web technology will probably will be making some call to a backend service, and we have kind of same implementation for our meeting rooms service. So again, a save instance function accepting an instance and posting it to backend. So if you're not using interfaces, as a side note, a good practice for an API is to be consistent and use the same naming, so that someone using a service knows how to save, how the save function is called based on other services that he already touched. But we can enforce these namings and the naming conventions using an interface. So I created an interface, iCreatable, to enforce that I have this save instance function that I can call with a single parameter being the instance to be saved. Again, the any type here just to indicate that we should still be enforcing type safety at a later stage. So the iCreatable, we want to apply it to both the car service and the meeting room service. So this save instance function needs to be able to accept both a car and a meeting room. So what we learned from the sum function is that we can use this syntax to make the interface a generic interface. So this means that we can use the iCreatable interface, pass it a certain type, so that it knows that the instance that is being passed to the save instance function is of the same type that is being passed to the generic interface. So that means for our car service, if it implements the iCreatable interface for the type car, that the TypeScript compiler in this case will enforce the save instance function and also enforces that the first parameter, the instance, is typed as a car. The same applies to the meeting rooms service. So the iCreatable meeting room interface is being extended. So the TypeScript compiler enforces us to use the save instance function, and the instance parameter must be typed as being a meeting room. If we were using the meeting rooms service in our code somewhere else, and we would call the save instance function with a different type, so maybe a company instance, for example, then the compiler would start complaining because we explicitly enforced it to be of a certain type, being the generic type that we passed it to the interface. So this is basically quite the basics of generics and more specifically generics in TypeScript. I think this can be extrapolated to other languages as well. I think in Java this should be possible. C# it should be possible. So basically the main thing is that we can bring code to a higher level, make it more reusable, given the sum function, for example, and it also allows us to have stricter typings in the code, and which translates to fewer bugs when going to production. So to make something generic, we just need to bring in the magic T. It doesn't have to be the letter T specifically. It could be any letter or even a word that you're using. I've noticed in open source projects that the letter K, the letter D, the letter R are also used very often. The main important thing is the bracket syntax with the type in it, and it should then come back at a later point in the code. Something I want to recommend, a tip that I want to give is to make sure what the generic type is about. T doesn't really tell anything about how it's used. So if you're able to make T more explicit about what it is, it's basically the same as having a good naming convention for your functions, for your properties, for your parameters. Also having a good naming convention for your generic types is also recommended. So T instance already tells me that this is a generic type being used to type a certain instance of something. T control value tells me already that the type is being used to type the value of a form control, for example. So this will help other developers basically for the same reasons why you are using certain naming conventions for properties, functions, and other stuff. Also, something that is possible is that you can combine multiple generic types and even use it as a return type of a function. So the sum function accepted a single generic type and returning a number, but you can also use it to type the response that is being returned. So in this case, we have a mapping function doing some mapping magic internally, where this T response is being used to type the response parameter, and the map result, the T map result type, is being used as the return type of the function. We went through examples of a function properties as well, I think, and interfaces, but this also applies to classes. So using the same syntax, we can create classes and make them generic to make reusable classes. So in this case, we have the mapper class, which has a domain type and a DTO type. So with some, again, highly reusable mapping logic. So the cars service, for example, can extend this class, the mapper class, being for the T domain. So for the domain type, we pass it a car, and for the DTO type, we pass it the car DTO type, which tells the compiler, okay, when you're using the cars service and you're calling the to-do function, so this car is passed to T domain. T domain enforces the toDTO function to have this parameter of the T domain type. So a car should be passed as a parameter to the domain parameter. So when we call this to-do function, this object has to match the car interface, otherwise the compiler would complain. And also the car DTO const in this case will immediately be typed as the car DTO. So we have our type safety later on. Now let's step up our game, and we can start using operators to make it even more generic and powerful. So first thing is the extends operator that we can use. So we have the generic type T right here, but as you can tell from the implementation, we require the item being passed to have a length property and a value property on the length property. So what we need is a function or our types being this strict to only allow items that implement this, because otherwise we would get a runtime issue telling us that the value property is that we are trying to access the value property of the length property. So for example, for the so the doors right here, there is no length property, there's no value property. So if we would be passing this as a parameter to the log length function, this would pass compilation because T is not limited. But at runtime, it would cause an issue because there is no length property of which we can extract the value property. So this is an issue right here. The other const matches the property, so this is fine. So what we would do right now is create an interface. I have length, for example, which enforces the length property of the type being an object with a value property having a number. So the log length value function, we need to tell T that it should only allow items that match this interface. So T should extend I have length. And this makes it impossible for us to pass the A here again, because then we would get a compiler error stating that A doesn't match the constraint of I have length, because A doesn't implement the length property and that length property doesn't implement the value property. So this would still be an issue on this line of code, but the issue is being thrown at compile time while we are developing our code and not when the code is in production. A second operator is key off. We can use this to limit something to be like the name states, being a key off something. So going back to our cars with the brand, model, and door count property, we have this car again, and a function logging the property of the item that is being passed. So this is a non-generic function, meaning that we can pass it any item that is basically an object and accept any property name, just any string value that could be a property name on the item that is being passed right here. So this means when we use this function, if we pass it the car and we tell it to log the brand property, this is fine, because we know this brand property is on the car interface and the car instance. If we call it a second time, passing it the car again, but then with the property name set to factory location, this is fine for the compiler because this is a string. It accepts a string. So the function continues and it would try to log the value of item.factory location. So for the compiler, this is fine, but we know as a developer, this shouldn't be possible because factory location is not a property of the car interface. There won't be an issue, there won't be really an issue in production because this would return undefined. But then again, we want this to be more type safe, so that if we are using this factory location parameter, we want to make sure that it throws us an issue while we are developing the code. So that we can fix it before this ends up in production and maybe cause a runtime issue. So if you want to create a type safe property logger, we include the generic again. So the object typing right here, we bring it to the generic type that it should extend that interface. So we know the item, this is still typed the same way as here, but right now we can use T to tell the compiler, okay, so whenever a property name is being passed right here, we know what T is because it's passed as a first parameter. We want this value only to be a key of that type. So if we pass it the car instance, the car item, this is now limited to only the key of T or the key of this type being a car, so we can only use brand, model, or door count. So this was fine before, this is still fine, but now it's type safe. The issue that we were having right here with this not type safe implementation is that factory location is not a property of car. So this would throw again during compile time and stating that factory location is not a key of the car interface. So this is what we want to achieve right now, making this again more type safe code and more reusable code to help other developers of the team develop better and safer code. So this is basically a very quick introduction to generics. I could have gone a lot deeper on stuff, but this is basically a first step to step up your game and make more reusable code to develop smaller applications supporting the same functionality.